All right, so today we're going to start by taking a look at partial fraction decomposition. And so it is something that we're going to start with some things that we know, just like we normally do. We'll talk about how this is new, but we're also going to talk about when are you going to see this again, right? Because I think sometimes we learn these new things and we're like, oh, when am I ever going to use it again? And perhaps not in real life, but as STEM majors, there are certain courses that we are required to take. And so I just want us to kind of know like when things might start to show up again. Okay. All right. So let's start off with a very classic problem. All right. I've got 1/3 and I want to add it to 1/2. I don't think there's anyone in this space who would tell me that this is going to be 2/5. Maybe we all thought that back in the day at some point. We just kind of like add across, right? What would we do instead to help us find an answer?
Make the denominators be equal so we can add them.
Good. Okay. So what would I do to the first fraction to make it have a denominator that is the same as the second fraction?
You'd multiply the top and bottom by 2.
Mm-hmm. And then looks like maybe the second one would be 3/3. Yeah, then we get 2/6 plus 3/6. And now when we add, what do we get?
5/6.
Yeah, we get 5/6. All right. So nothing spectacular here, but a reminder that a lot of the algebra that we're going to do goes back to the same idea as what we know how to do with numbers, right? So just because we throw some letters in there doesn't mean that like everything, is completely different. It just means that some of the structures are the same. We just have to practice seeing those structures. Okay, so we're going to be using this idea of common denominators today. But we're also going to be looking for the least common denominator, right? So least common denominator. And then we're also going to be using something I like to call fancy ways of writing 1. Like literally the number 1. Okay. So one of the ways I could write 1 might be 2/2, right? Another way that I could write it might be 3/3. And we're going to get even fancier than that as we apply what we know about fractions and least common denominators to this new idea of partial fractions. So what's new? We're going to be applying these concepts to fractions with variables. All right. So, okay. So I want to show us an example that is a pretty classic one of what you might see the skills that we're going to learn today, but in a later course. Okay. So sort of similarly to factoring, how factorings kind of come up again and again in these bigger problems, partial fraction decomposition is something that we see again later in our careers. And in particular, we see them in Math 151, or we call that Calc 2. Okay, so if you are planning on being an engineering major or a physics or chemistry major, I'm not sure if computer science needs to take 151. My guess is yes, but I cannot remember. And if you're thinking about being a bio major, depending on where you transfer, if you're looking for a UCSD transfer, they do want Math 151, okay? So it is something that you will see again, likely in the context of a higher math class, all right? And so some of these symbols might be familiar to you and some of them might not be, and that's okay. So we have this symbol here, which we're gonna learn a lot about. It is called an integral symbol and it pairs always with this dx. And so when we're looking at a problem like this, we would say, oh, wouldn't life be nice if I could factor that denominator, right? So if you were to take a look at all the things that are complicated, but maybe just zoom in on this x squared minus x minus 6, you might notice that you can factor this into x minus 3 and x plus 2, okay? Now, the reason why we want to do this is because in order to solve this problem, it might be easier if we could write it as one fraction plus another fraction. Okay. Now, how do we find the A and B values? That is really our goal, okay? So finding this A and finding this B is going to be what we're focusing on in our class, okay? If we have time, we can come on back and sort of like work through the entire problem, but I just want to kind of set the stage that our goal is to get to something like this so that we can have this plus all right. So this is very big picture. This isn't about 2 semesters for you folks, maybe even summer school if you're feeling super, super like you want to just get all the math out of the way, or you're really enjoying the math. You could certainly be in Calc 2 this summer because we will be working through Calc 1 in the spring. Okay, so just kind of keep this as food for thought that that's when you're going to see it again. We won't really see the structure again in Math 150, but rather we're planting the seed for something a little bit further in the future. Okay. All right, so let's take a look at some foundational skills. All right, we're gonna take a look at some factoring and take a look at the least common denominator, and then figure out some systems of equations. So everything on this page is meant to be like very usable chunks of what we're all going to string together. Okay, so let's take a look at the factoring here. We've got an example 1 and we've got an example 2. I would say that one of them is easier to factor than the other one. Which one is it and why?
2, because factor with the greatest common factor, which would be x.
Yeah. And when we say easier, I think sometimes it's nicer to think about it like it's more, it takes less ink to write. Maybe it takes a little bit less, it takes fewer steps, okay? So recognizing that we have a common factor here, x, and when we factor that out, we get x minus 4, right? All right, now, factoring, right? Factoring and thinking about how we deal with a situation when there's a 2 in the front, okay? So I think we've talked about factoring by grouping, and I wanted to show a different method here in case this is something that you find a little bit more useful, okay? So one of the ways that I approach factoring is I think about what my A value is, what my B value is, and what my C value is, right? So in this case, A is 2, B is 11, and C is negative 21. And so what I do is I set up an X situation where on the top, I put the B value, and on the bottom, I put A times C, all right? And then what I'm trying to find is I want a pair of numbers that add to make B and multiply to make AC. So if we apply this to the numbers we have, our B is 11, our A times C is negative 42. Okay. So let's come up with a list of factors for 42. So I know 1 times 42 gives me 42. 2 times 21 gives me 42. Does 3 go into 42?
Yes, 14.
3 goes into 42 14 times. All right, are there any other factors for that?
Um, 6,
6 and
7.
yeah, okay. And then I think that's it. All right. And so you'll notice I didn't put any plus or minus signs here, but of the pairs we have, which one of those can we add in some fashion to make 11?
Negative 3 and 14.
Yeah. If I take a look at 1 and 42, there's no way I can make 11 by adding or subtracting. Same thing with 2 and 21, same thing with 6 and 7. 6 and 7, I get to 13, which is kind of close, but I don't get to 11. And so if I take this pair right here and I put those on the sides, 3 and 14, remember I want them to add to 11. So 14 plus a negative 3 will give me 11. Okay, so this is sort of a useful structure to help you find those numbers if that's something that you're not as comfortable doing. Okay, now the second step to this is sort of a box situation. Okay, so I kind of draw out a little box and I take the first term in my equation and I write that in the top left-hand corner. Then I take the 2 numbers that I put in the side here, and I'm going to put one of them up here and one of them down here. And I'm going to make sure that they are linear terms. So in other words, I don't want to put a negative 3, but I want to put a negative 3x. And I don't want to put a 14, but I want to put a 14x. Okay. Now I'm going to leave this last box blank for right now, because that's actually going to be our check to see whether we did it correctly or not. Okay. All right. So here's how this is going to work. Our goal is to fill out the outsides of this. So what can we multiply to make 2x squared?
One. Is that
Yeah.
what you mean?
Well, like 2x squared times 1 makes 2x squared. Sure. What else can we multiply to make 2x squared? Two times x squared, for sure. Okay. What else can we multiply to make 2x squared?
X.
Yeah, an x and a 2x, right? Now, at the end of the day, what we want to do is factor this. And so we have something kind of like this. And so what we're doing is each of these outsides is going to correspond to one of the factors. All right. So 2x and x. If I just look at this rectangle and I think about what I know about area, if I take something that has a length of 2x and a width of x, then the area of that rectangle is 2x squared. Okay, So you saw something kind of like this in one of the Desmos activities, but I wanted to show how you could actually use it like without Desmos. So if you're looking, let's look at this rectangle over here. This is the area of this rectangle is -3x. Now, I know that area isn't negative, but let's just go with this negative piece for a little bit. Do I know how long this side of the rectangle is?
X.
Yeah, that's going to be X, right? Because it's the same as this one. Okay, if this is X, how long does this have to be to give me an area of -3x?
-3.
Yeah, so we'll put a -3 up here. Okay. Now let's go down to this lower left-hand corner box. I have an area of 14x. How long is this side?
2x.
2x. So how long does this side have to be?
7.
Good. So we'll put a +7. Okay. So right now, what I'm suggesting is that the factors are 2x minus 3 times x plus 7. Meaning I would have like 2x minus 3 and x plus 7. So how do you know if you did it correctly? Well, how long is this side?
7.
7. How long is this side?
-3.
So what's the area of this box down here? Yeah, -21, right? Is -21 the very last number we had here? And if it is, there's your self-check. That's how you know you factored it correctly. So we can write our factors now as 2x minus 3 and x plus 7. Okay. So if you're not feeling great about factoring, this is something that you can try a few examples. You can pop on over to office hours. I'm happy to help you like talk through this process. But the more you do of these questions, like the more you practice this process, the faster it does get. Okay. So that even if you're like, oh, this one problem took so long, the more you do of them, the faster they get. Okay. And I will 100% guarantee you that factoring is not going to go away at all this entire year that we're together. All right. So that is both bad news and good news. All right, so we've done a little factoring review. Let's talk a little bit about this least common denominator, okay? So we want the least common denominator because it keeps the numbers smaller. All right, it keeps the numbers smaller. And the smaller numbers we have mean that it's going to be a little bit less ink and maybe a little bit less brain power to make that common denominator, but all the other calculations that go with it. Okay. So if we kind of go back to the first example, we did 1/3 plus 1/2, and we wanted a common denominator of 6. But what other denominators could I have had? Let's list out a few. What other denominators could I have said, let's make this as a denominator? I could have said 12, right? What else could I have said? $24. I could have even said 600 as a common denominator. That seems outrageously large for doing something with numbers like 1/3 and 1/2, right? It's not mathematically wrong, right? I could certainly do it with 600, But of these, perhaps the one that is most efficient is choosing the smallest denominator, or denominator of 6, right? What would be my least common denominator here? Ooh, okay, 8. It could also be 16, right? If I did 8 times 2, I would get 16. But if we have a smaller one, we should go with the smaller one, okay? We could have something outrageously large like 16,000. Again, that one is so extreme. It is more like a hyperbole, right? It is an exaggeration of not the least common denominator. But I think hopefully one thing that we'll walk away with is like, it's gonna be nicer for us if we use the least common denominator, right? The last thing I want to talk about is systems of equations. So we've been working a lot with systems of equations, but I want us to think about sort of different kinds of systems and how we might approach them, right? So last week when we met, we talked about systems with 3 different equations, 3 variables, and now we actually have 4 different variables and 4 different equations, okay? So take a moment. I'd like you to take, maybe let's give everyone 2 minutes and start to see if you can find any of the letters, A, B, C, or D, okay? So everyone's gonna have a different strategy, but let's kind of see what folks come up with. And then we'll share out some strategies and see if we can come up with like a good, set of strategies or ways that we might approach this as a class. Okay, so take about 2 minutes, see how many of those 4 letters you can find. All right, what are our thoughts? How can we solve for any of these 4 letters? Okay, so you took this equation, you got A all by itself for sure. And then what were you gonna do with that? Oh, so then you plug this into that first equation. Okay. So maybe one way we could sort of frame that is we took the 2 equations that had the same letter and we try to do something with them, right? And so I like that approach. We get A equals 3 minus 4C. And that's what you said. And now everywhere we see the A, we're going to plug it into that other purple equation. So we get 0 equals 3 minus 4C plus C. We get 0 equals 3 minus 3C. All right, so what does that make C? Yeah, so I'm going to add 3C to both sides, and then I get C equals 1. Perfect. Okay. What would be reasonable to find next? A. Okay. So which equation would you like to plug into to find A? Nice. I would agree. So 0 equals A plus 1. And so we can see that A equals -1. Perfect. Okay. Now, I bet we could do something similar with the other two, because this one and this one both have B and D in them, right? So maybe let's take these. Now, it looks like Ian used substitution here. Don't forget, you can also use elimination, right? And so what I'm going to do is I'm going to go ahead and take 1 equals B plus 4D. And I'm going to subtract the other one, 1 equals B plus D. And so I'll get 1 minus 1 is 0, B minus B is 0, 4D minus D is 3D. All right. And so that gives me what as a value for D? Exactly. We get D equals 0. And from here, we can find B. I think if we choose the top red one, right, then we could see that B equals 1. All right. So let me zoom in so we could sort of see this whole page right here. All right. I wanted to take the moment to kind of highlight these foundational skills, because as we move into Math 150 and as you take higher and higher courses, it's not always going to be so laid out like, okay, these are the things you need to walk in there. Okay. At some point, there becomes sort of an expectation that like, oh yeah, I do know how to factor. I do know how to find that least common denominator. But while we're still learning that, I wanted to take the time to say, okay, let's make sure we know each of these pieces. And then the goal now is, how do we tie them all together to solve a problem? Okay. All right. So with that being said, let's go ahead and take a look at the first of 4 different cases. Okay. So our first case here is we have non-repeated linear factors, okay? Non-repeated linear factors. This is very fancy notation, but all this means is that when you factor the denominator, you're going to get a bunch of linear factors. Okay. Now, if you get linear factors on the bottom, you're going to end up in your what we call partial fraction decomposition. You're going to end up with constants on the top. Okay. That's a lot of words. This is a lot of letters. Let's see what it actually looks like. Okay. So question like example 4 would be one where we want to think about, let's factor that denominator. Let's see what we get. Okay. And so let's start off by rewriting this line, 5x plus 16. We're going to leave the numerator alone for right now. And I'd like you to take a moment in the privacy of your own learning environment to factor that denominator, x squared plus 10x plus 6, plus 24, sorry. And when you have that factorization, go ahead and type that into the chat, okay? All right, we've got one answer in there. We get any other confirmations to make sure that that is correct? Yeah, okay. Okay, so the first step that you're going to do is you're going to factor the denominator, okay? Once you've factored that denominator, you're going to look at what your factors are. Are they linear or are they not? Okay. Now in this case, we have x plus 4, that's linear. And we have x plus 6, and that's linear. Since they are both linear, okay, and they're not repeated, meaning x plus 4 is different from x plus 6. Okay. What you're going to do is now you're going to split this into two fractions. You're going to write this as a over x plus 4 plus b over x plus 6. You've got one denominator here, another here. And since the denominators are linear factors, we only want to put a constant up at the top. Okay. Now our goal is to find out what a and b are. Okay. Once we found out what a and b are, we are good to go. We have our answer. All right. If I wanted to add these together, all right, so focus in on these right here. If I wanted to add these two fractions together, could I just add them the way they are right now? We get a plus b over x plus 4 plus x plus 6. Right, that would be making that same mistake, like 1/3 plus 1/2 is 2/5, right? We would just be adding those together. So what would we need in order to add these two equations or these two fractions together? Yeah, we need a lowest common denominator, right? So we're going to go ahead and make that lowest common denominator. What should we multiply the first fraction by? What should we multiply the second fraction by? Yeah, we're going to do x plus 6 over x plus 6, x plus 4 over x plus 4. Okay. So what we've done here is find the least common denominator. All right, now here's what we have. We're going to grab this first part, 5x plus 16 over the factors, and we're going to set it equal to that part. Okay. And so when we do that, we'll end up with 5x plus 16 over x plus 4 times x plus 6 equals, let's see, let's copy and paste that. All right. This denominator is x plus 4 times x plus 6. Is this denominator the same or different?
The same.
It's the same. Okay, what about this denominator?
The same.
The same. Okay, so let me ask you guys a question. What's x?
1.
How'd you know that so quickly?
Because you can basically eliminate the denominator and then just subtract 2.
Exactly, right? When all our denominators are the same, we don't even really need to worry about them to find the variable we want. We can almost simplify this to say x plus 2 equals 3. Now I know this has numbers and fractions and some letters, but it looks simpler than what we wrote down here. But the structure of it is the same, right? Instead of a 7, 7, and a 7, I have x plus 4 times x plus 6, x plus 4 times x plus 6, x plus 4 times x plus 6. Since all the denominators are the same, we can say goodbye. We don't want to worry about you right now. Let's focus only on the numerator, okay? So what do we have left then? We have 5x plus 16 equals a times x plus 6 plus b times x plus 4. Okay. Now remember, our goal is to find a and b. So you can definitely start distributing and collecting like terms, right? So we could do something like this. 5x plus 16 equals ax plus 6a plus bx plus 4b. How could I write two different equations from what I have here? It's sort of a tricky question, so it's okay if we're feeling stumped on it. Well, it turns out that one way that we can write two different equations is we can collect all the terms that have an x, and separately we can clump all the terms that only have numbers. And then we can write two separate equations. So we could write a yellow equation, 5x equals ax plus bx, and 16 equals 6a plus 4b. Now I argue that we can make this first equation, the yellow one, even simpler. Anyone have any ideas on how we might be able to do that?
You could factor out the x.
Yeah, you could factor out an x, and then you could even divide it away because it's on both sides and end up with 5 equals a plus b. Okay. So now we have this red equation, 16 equals 6a plus 4b, and 5 equals a plus b. All right. So I'll give you folks a moment to go ahead and see what you can find for A and B. All right, we refreshed our memories. We didn't learn, but we refreshed our memories on both substitution and elimination last week. So let's take a couple moments. Let's apply that right now to find out what our A and B values are. Okay. All right. What are some thoughts? How would we approach solving this system of equations?
You could do a substitution with the first one, the 5 equals AB. You could just either minus the A or the B to get something to plug into the other equation.
For sure. Yeah, we could use substitution here. Anyone have an answer?
So far, I've only gotten B equals 7. Then
So B equals 7. I think we can do a quick substitution, maybe back into this first one. You get A is -2, right? Now what that means is we have our setup for our answer, and all we would need to do is go ahead and put back in -2 for A and 7 for B. All right, so what this would look like is we would say that 5x plus 16 over x squared plus 10x plus 24 is going to equal -2 over x plus 4 plus 7 over x plus 6. And this would be my A and my B value. And these would be my non-repeated linear factors. Okay. If you wanted to check your answer, you could go ahead and add these two fractions by making a common denominator, working out that numerator, and I bet you would end up with 5x plus 16. Okay. Now, we're going to be doing a lot of these. And so substitution and elimination, it's really good practice. And sometimes we're going to be forced to use that. Okay. But sometimes there is a shortcut that we can use. This doesn't work all the time, but I want to show us what it looks like so we can start to think about using it if we can. Okay. So if you don't love the elimination and substitution, which are still really important skills, this is a different method that you can try. Okay. So we're going to cleverly pick some numbers. Okay. So let's pretend, let x equal -6. Okay. And we're going to plug -6 into this equation everywhere we see an x. So help me out. What do I get for this first term? We get -30 plus 16 equals A times what? 0. Oh, that's nice. Plus B times what? -2. Okay. So if I add what I have on the right-hand side, or left-hand side, I get negative 14 equals negative 2b. All right, what's b equal? 7. Perfect. All right. This felt to me like a much more efficient way of getting to one of the letters. Okay, but all it got us was one of the letters. How could I use this same method to get the other letter? What would be a clever number to choose for x?
-4.
-4. Okay, so let's see what happened. I chose -6, and that made one of the factors go to 0. And because that one factor went to 0, I immediately got one of the other letters that I wanted as the only variable in the equation now. Well, if we try that same idea, remember we have to plug it in everywhere we see an x. If I let x equal -4, this b term is going to go to 0. So if we plug in -4, we'll get -20 plus 16 equals a times 2 plus b times 0. And that's going to give -4 equals 2a. And we get a equals -2. Okay. So a clever trick, if you will, to get to the same answers that we had up here. You can also get the same answers using substitution or elimination. Okay. Either way, sometimes in a lot of the later problems we'll see, we actually combine both methods. We get as many as we can get using the shortcut, and then the rest of them we use substitution or elimination to find out. Okay. There is an example 5 squeezed in here. I will leave that to you to do on your own, but I will let you know that some numbers you should be looking for. There should be a 1, a 4, and a -5. That corresponds to the numerators for that. Okay. All right, so I'm going to leave this up on the screen. I think this is a good time to take a break. When we come back, we're going to take a look at 3 other cases. And one of the things I really want us to walk away with today is getting to the setup point, making sure we know how to set things up. That's going to be part of what I ask you on Wednesday. Like, I want to know that you can set things up, which means you have to know how to factor. Okay. So let's go ahead and take a break right now. It is 10:36. So let's be back at 10:46, and then we will pick up right here. Okay. See you folks back here in a little bit. All right, folks, we're gonna get started again. So just to reiterate, before break, we took a look at the non-repeated linear factors. That's one of 4 cases. And just so we can kind of see what the other cases are, because there's a total of 4 different cases. Okay, we have case 2 here that has repeated linear factors. So it's a little bit different here. All right, we've got repeated linear factors, which means that maybe when we factor, we get the same factor more than one time. And then the last 2 cases we're going to take a look at are going to have non-repeated irreducible quadratic factors as one. And then for case 4, we'll take a look at repeated irreducible quadratic factors. Okay, so some of this language we've seen before, and I kind of purposely brought it up earlier because I wanted us to be familiar with the phrase, not just a quadratic factor, but that word irreducible. Okay. So let's get back to case number 2, where we have the repeated factors. And so a couple of things I want to point out here that are a little bit different is that when we have the same factor, so ax plus b, if we have it twice, then we're going to have to write it as 2 separate fractions. One where it happens one time and 2 where it happens the second time. All right. And as many times as it repeats, we just write more fractions. However, what does not change is we'll still have constants up on the top. Okay, so these are still constants, and these are linear factors. Okay, so we're going to take a look at example 6 here. All right, we've got negative 5x minus 19 over x squared plus 4x plus 16. And the first thing I'm going to ask us to do, just like I did in the other problem, is for you to go ahead and factor the denominator of your of this given fraction. Okay. X plus 4, x plus 4, exactly. Okay, so we've got these factors, and one of the things we want to notice is last time we had like an x plus 4 and an x plus 6, but this time we have 2 of the same factors. And so if we have 2 of the same factors, the way we're going to split these is we're going to have a over x plus 4. Right? That's going to be very similar to this one, but then we're going to have a second fraction that has x plus 4 squared on the bottom. So b over x plus 4 squared. We've got our constants at the top, and we've got our linear factor that happens one time as well as the second time it happens. Okay. All right, once we find this, this is what we call the setup. But if we wanted to add these fractions together, we would need a common denominator. And so I'll ask you the same question I asked you last time, which is, what do we need to multiply by or to get that least common denominator?
For A, it would be x plus 4, and then for B, it'd just be 1.
Really, really nice, right? X plus 4 times x plus 4 will get me x plus 4 squared. That means I don't have to multiply the second one by anything. I can actually multiply it by one of the simplest ways of saying 1, which is 1 over 1. Okay. Now I wanted to point that out because sometimes we go overboard and we say, oh, this one has an x plus 4 squared, so I'll multiply this one by an x plus 4 squared, and then this one by an x plus 4, and all of a sudden we have like cubes going on in our equation, and that's just because we chose to do a common denominator, not the least common denominator. Okay. So always go for the least common denominator. But once you've done that, if your denominators are the same now, so x plus 4 times x plus 4, x plus 4 times x plus 4, x plus 4 times x plus 4, then you can just write what the numerators equal. So negative 5x minus 19 equals a times x plus 4 plus b. Okay. All right, once we have this, we can either set up a system of equations using substitution or elimination, or we can cleverly choose some numbers, okay? So it's really up to you. What would we like to try? Would we like to try substitution or elimination, or picking clever numbers? All right, looks like maybe pick a clever number. So let's let x equal -4 and see what happens. All right, so we get 20 minus 19 equals a times 0 plus b. Yeah, that seems pretty clever to me. We get b equals 1. Okay. Is there a second clever number that we could choose? What makes you say 0?
Never mind.
Yeah, before there was like another x term here, right? So we had like x plus something. If we had an x here, I would say, yeah, 100% we could choose 0. Okay. You have a few choices here. I think that one thing you could do, let's take a moment and see what it would be like if we wrote a system of equations. So take a moment, let's think about, I think we did yellow and red last time, right? So -5x minus 19 equals ax plus 4a plus b. What two equations could we write from here?
You could do -5x equals ax, and then -19 equals 4a plus b.
Exactly. Yeah, we could definitely do that, right? We've got our ones with the x. We've got our ones that just have numbers, right? And then we're able to split those into two equations. All right. Well, you know what? We already have a number for b, right? We have b equals 1. If we put b into this equation, I bet we can find a. So -19 equals 4a plus 1, or -20 equals 4a, or a equals -5. Right? So there's no set way to necessarily find all the different values. Some people like to choose clever numbers, but sometimes there aren't enough clever numbers to choose. So we might need to go back to a different method, and all of that is okay, right? That's why it's so important for us to think about like, okay, what are all the tools that I have? Okay, I feel comfortable using substitution. I feel comfortable using elimination. I feel comfortable choosing a clever number. And the more comfortable we are with these different types of strategies, the easier it'll be to say, oh, maybe I should try a different strategy, right? Whereas if we only have one strategy and that one doesn't work, then at some point we're kind of out of luck, right? All right, so as our solution, we would write -5 over x plus 4 plus 1 over x plus 4 squared. And that, my friends, would be our solution. Okay. How we doing so far? I feel like we're pretty quiet today, and it's kind of hard for me to gauge like how much we are or are not understanding. So even if you want to send me a direct message and kind of let me know.
I have a question on the splitting up into a system of equations. I don't understand like why you can do that.
Okay, so if you think about the way this is written, it says that anything with an x on this side has to be equal to anything with an x on this side. Because that's like our like term, right? If it has an x and they're on different sides of the equation, they must be equal to each other. We can sort of think about it like if we did a maybe simpler statement. If I said -2x plus 5 equals ax plus 5, what does a equal?
-2.
Yeah. Right? -2 because the linear parts of the equation have to be equal to each other and the constant parts have to be equal to each other. So we're just extending that idea to where there's more unknowns, but we have the linear parts equal to each other and then the constant parts equal to each other.
Okay, I get it. So the A and B are kind of like considered to be the constant, or like what we're using in order to find a constant. So
Yeah.
that's why we're able to set it up.
Yes,
Okay, thank you.
exactly. All
I have
right.
a question.
Yeah, for sure. What's up?
So, when we were multiplying by the 1,
Mhm.
how did we like cancel out x plus 4 squared by 1/1?
We canceled them out because all of the denominators are equal on both sides. So in other words, I think we talked about this earlier. If you had an equation like this, x over 7 plus 2 over 7 equals 3 over 7, I think we would all agree that this has to be 1. But we didn't actually use the denominators. We just used the fact that the
Oh,
denominators are the same as each other.
because we didn't use them.
Yeah.
Okay.
Does that make sense?
Yeah.
Okay, cool. All right. So same thing. I'll leave example 7 here as one that you can do on your own. I feel like it would be helpful to get the answers though. There should be a 6 and a -5 for number 7. Okay. The order might depend on how you set yours up, but one of the constants should be 6. The other one should be -5. All right, so let's take a look at case number 3. So case number 3 talks about non-repeated irreducible quadratic factors. And the key term here is this irreducible. Okay, irreducible meaning that there are no real numbers that you can factor this into. Okay, so let's just write this here. This means that cannot be factored with real numbers. Cannot be factored with real numbers. All right, so one of the things that we'll notice here is you've got a quadratic term in the bottom, right? It looks very fancy, but it's really like ax squared plus bx plus c. And then on the top now, though, we actually have something slightly different. We don't have constants anymore on the top, but how would you describe the numerators? What kind of terms are they? They are binomials. Be a little bit more specific though, because I just said they're not constants. So what kind of terms are they? Yeah, these ones on the top are all linear. Okay, so if you have an irreducible degree 2 on the bottom, on the top now, we're not just going to put an a, we're going to put an ax plus b. We're going to put a linear term up there. Okay. So let's try example 8 to see what that might look like. All right. So we've got this f of x. We're going to keep our numerator the way it is. We're going to factor our denominator. All right. Now, I'm sure there are some of you sitting right now in your learning environment being like, ooh, I don't know how to factor this. But if you can factor this, x squared plus 5x plus 4, you can factor that, okay? So maybe let's start with this one. What does x squared plus 5x plus 4 factor into?
X plus 4 times x plus 1.
Good. Okay. Now that's if I'm multiplying to make an x squared, right? X times x gives me x squared. How could I modify this so in the front I get x to the 4th?
You could either swap it in with like a different variable temporarily, or just do x squared to the second power.
Sorry, say that again.
So basically you could just do x squared with a parentheses squared again.
To make the x to the 4th?
Yeah.
Yeah, exactly, exactly. And the way that that impacts our factoring, because everywhere we saw an x, we're putting in x squared. X plus 4 is going to become x squared plus 4. And similarly, x plus 1, when we factor it under the 4th degree, will be x squared plus 1. Okay. So factoring quadratics, super useful because they can help you factor a lot of other degrees as well. Okay. Now, x squared plus 4, that does not factor under the real numbers. And so what I have here is an irreducible quadratic factor and another irreducible quadratic factor. So I'm going to set up the first fraction, x squared plus 4. What goes on the top?
Ax plus b.
Great. We've got a quadratic on the bottom, so we need a linear on the top. And then for our second fraction, we have a denominator of x squared plus 1, still quadratic. So we're going to need a linear factor here, right? Instead of ax plus b, we'll just move along the alphabet. We get cx plus d. Okay. So if I said, hey, set this up, you would be done with your setup at this point. Okay. But I want us to solve this, right? So if I ask you to set up, this is a great place to stop. But if I want you to solve it, now we have to find out what is that lowest common denominator. All right, so what do I multiply the first and second fractions by to get a least common denominator?
On the left, it would be x squared plus 1, and then on the right, x squared plus 4.
Nice. Okay. Now let's double check. If all of the denominators are the same, we can sort of ignore them, right? So we have x squared plus 4, x squared plus 1, x squared plus 4, x squared plus 1, x squared plus 4, x squared plus 1. Those all look the same. So we can create an equation from just the numerators. And we'll get x squared plus 3x plus 1 equals, I'm going to be really careful about putting in parentheses right now, ax plus b times x squared plus 1 plus cx plus d times x squared plus 4. Okay. All right, so what clever numbers can we choose to make some things go to 0?
I don't think you can pick any clever numbers.
Yeah, so remember I said earlier that like clever numbers are great when you can use them, but sometimes we can't use them. Okay, this is an example of one where we can't use our shortcut. And the reason is you can ask yourself, is there a real number that I can plug in for X to make this go away or go to 0? And there is no real number that we can put in there. Okay, same thing with this one. I can't square anything and get -4 in the real numbers. So what does this mean for us? It means that we're going to have to multiply a bunch of things out, and we're going to have to be really careful about our work. So we're going to distribute over here, and then we're going to do the same thing for the second set of binomials. Right. And so let's see what we get. So we get ax cubed plus ax plus bx squared plus b. That's the first one. Plus cx cubed plus 4cx plus dx squared plus 4d. And on the other side, oops. I'm gonna bring down that. Okay. I would always double check your signs to make sure that you know, like, all right, did you distribute everything correctly? Did you lose any letters along the way? Okay, this is a good chance to like stop and check your work before you continue on. But as we're going through, let's start thinking about how many different equations we should have based on the right-hand side. Okay, in other words, let's find some like terms and clump them together. So if I highlight this term, ax cubed, what else should I highlight?
Cx cubed.
Perfect. Okay. Anything else that I want to highlight in yellow? I don't think so. I don't think there's any other cube terms. All right. What about if I highlight bx squared? What else should I highlight? Perfect. Dx squared. All right. What if I highlight ax? What else should I highlight? 4cx. Okay. What if I highlight b? What else should I highlight? Yeah, we can highlight that 4D at the end, right? So don't be fooled. I know that a B is a different letter than a D, but both of them are constants, right? They don't have any X's with them at all. And so based on this right-hand side, I should have 4 different equations. And so if I start to write them out, I'm going to get ax cubed plus cx cubed. I'm going to get bx squared plus dx squared. I'm going to get ax plus 4cx, and I'm going to get b plus 4d, right? But now I have to figure out what they're equal to. So what is that blue equation? What should I put on the left-hand side of the blue equation? Perfect, right? We look on the other side of the equation, which one is only the number? It's just 1. All right, what goes on the other side of the green equation? Perfect, right? We look for the term that is linear. We got a 3x, perfect. All right, what goes on the other side of the orange equation? Brilliant, you guys are way ahead of me here. What goes on the other side of the yellow equation? Yes, okay. Now this is why I sort of indented everything, because ideally I would actually put a 0x cubed in the front to remind myself that even though there's no x cubed, what that means is it's a 0x cubed, right? Okay, well, we can streamline this equation, this set of equations, right? We can actually write this as 0 equals a plus c, 1 equals b plus d, 3 equals a plus 4c, and 1 equals b plus 4d. All right, so I still have my yellow equation, but I divided everything by x cubed. I still have my orange equation, but I divided everything by x squared. I still have my green equation, but I divided everything by x. And then my blue equation stayed the same. Okay. Now, ordinarily, at this point, you would have to solve for a, b, c, and d. But if you scroll back up into your notes a little bit, you might notice this is the same example we used for systems of equations practice earlier. And in fact, we found a equals -1, b equals 1, c equals 1, and d equals 0. Okay. So we found our values, but we're not done until we put them back into our equation. So we have our actual solution, like we know what the A, B, C, and D mean. And so if we go back up here, and put in our numbers, we'll get -x plus 1 over x squared plus 4 plus x plus 0 over x squared plus 1. All right, you don't have to write this 0 if you don't want to. I only put it there so we would know like the D got plugged in as well, but it was just a 0. Okay. So as you start to think about the exam on Wednesday and for the quiz that you're doing for Wednesday as well, one of the really important things is not just all the algebra, but the setup. Like, how do you know how to set this up? And what kind of strategies do you have for solving those systems of equations, right? When can you plug in a sort of nice, clever number? When can you not? And if you can't, what do you have to do in order to find the values you're looking for? Okay. All right, any questions on this one before we move on to the last example here? All right, so let's move on to our last case here. All right, we're looking at repeated irreducible quadratic factors. And so this is very similar to the repeated linear factors, that if we have a quadratic factor that pops up more than one time, the numerators are still linear. Okay, the numerators are still linear. And so let's take a look at this example right here, right? So we'll start off the same exact way. As I'm writing the numerator, I'm going to ask you to factor that denominator. And remember, if the factoring of something to the 4th power is a little scary, you can try writing it just as a quadratic, factor that, and then everywhere you see an x, you can put an x squared.
It's x squared plus 1.
Yeah, it's just gonna be x squared plus 1, and then x squared plus 1, right? So unlike the other question we looked at, this one has the same factor happening more than one time. And so when we set up our partial fractions, we're gonna have x squared plus 1 as one of the denominators. What's the second denominator gonna be?
X squared plus 1 squared.
Perfect. All right. So we've got x squared plus 1, and then the second one is the doubling of the first one, but both of these numerators are going to be linear. Okay. Now, in some ways, I think the repeated ones are a little bit easier to find that least common denominator. Not all the time, but sometimes. So what should we multiply both fractions by?
Only the ax plus b by x squared plus 1.
Yeah, only that first one needs to be multiplied by something. My screen is frozen. Hold on. There we go. All right, so x squared plus 1, x squared plus 1, and then we'll have 1 over 1. You don't have to write that, but sometimes I think convincing yourself, okay, I did multiply it by something, it just was 1, so it didn't change anything, is an important reminder, right? But once all the denominators are the same, now we can write an equation that is just the numerator with carefully placed parentheses. Right. All right, let's see what we get. We get 5x cubed minus 3x squared plus 7x minus 3 equals ax cubed plus ax plus bx squared plus b plus cx plus d. All right. Let's see. We've got ax cubed. Now let me look for my quadratic terms. All right, let me look for the linear terms. Let me look for the linear terms. All right. Based on this, what do we know?
We know A equals 5, B equals -3,
Great.
and C equals 7, and D equals -3.
I think I got a different value for C. So let's see, the green equation would be 7
Oh, yeah, 7.
A plus C, right? And since we already have A, that makes C pretty quick to find. I think we should have C equals 2. And we could do the same thing with the blue equation, right? -3 equals B plus D. But I already know B is -3, so D is going to be 0. So even though this looked like it was going to be way harder and we couldn't really use a shortcut, the actual system wasn't too bad. Okay. And so our answer is going to be 5x minus 3 over x squared plus 1 plus 2x over x squared plus 1 squared. And this time I didn't write the 0 for D, but there you could write a plus 0. That would be okay. All right. So folks, this brings us to the end of partial fraction decomposition. I would say that as you prepare for Wednesday's exam, keep in mind the 4 different cases that we saw. All right. But this kind of algebra, like all of the factoring, being able to make sure that your work is accurate along the way, this is something that I do want us to be able to show individually. Okay. And the reason why I want that to be something we're all comfortable with is because we're going to start to see a lot more algebra in the next course in Math 104 and a lot in 150, but it's going to be sort of, in order to do the work we want to do, we have to have a pretty strong algebra foundation. Okay. So I don't want this to seem like a gotcha situation, but I want to be really clear that like being able to do this kind of work independently is something I'm really looking for on Wednesday's exam. Okay. So let's go ahead and stop this video.